Hello everyone, welcome. This is November 2022. This is paper 1 and this is time zone 1. Let's have a look and see what we can do. Question 1. Kachina stands at point K, the top of a 218-meter vertical cliff. The base of the cliff is located at point B. A ship is located at point S, 1,200 meters from Kachina. This information is shown in the following diagram. All right. Part A asks us to find the angle of elevation from the ship to Kachina. All right. So few words that we have to look out for. First, there's this directionality. Where are we going? We're going from the ship to Kachina. And then what are they asking for? They're asking for the angle of elevation. So angle of elevation, remember, is, let me just draw maybe, let's say some base. Angle of elevation, we are looking up from the horizon. So if this is the horizon, what is the angle that we need to sweep through if we wanted to, let's say, look up or reach our target? So in this case, angle of elevation, this theta value in here. So here's our angle of elevation in this diagram. What is the angle of elevation from the ship to Kachina? Well, here we have two side lengths. We have this hypotenuse and then this opposite side length. So in this case, we can actually use right angle trigonometry. What do we have? We have the opposite, and we also have the longest side length, which is hypotenuse. So remembering sa, ka, toa, in this case, we have sine because we have our opposite side length and the hypotenuse. So let's write this out. This is sine theta is equal to opposite over hypotenuse. In this case, we don't know what theta is, but we know the opposite is 218 and the hypotenuse is 1200. Now we can go ahead and isolate isolate theta by writing the inverse of sine. But we can also, if we want, just end solve this right here. Either of those should work. So let's go to the calculator and find out this value. So let's go and use inverse sine in this case. So inverse sine, and then we'll set up a fraction which shows our ratio between opposite and hypotenuse. Make sure you're in degrees. And we have an angle of elevation of 10.4669 or 10.5 degrees to 3 significant figures. So let's write that up. Theta is equal to 10.5 degrees. This would be our angle of elevation. 2-mark question, you'd want to make sure that you show the ratio and then what you're substituting and then the answer itself. If you just put 10.5, you'll probably just get A1 answer mark. All right. Question B. Find the horizontal distance from the base of the cliff to the ship. Okay. So we want to find this side length right here. A few different ways we can do this. Since we know this angle of elevation, we can go ahead and actually use right angle trig, or since this is a right angle itself, we can actually just use the Pythagorean theorem and say a squared plus b squared equals c squared. So in this case, I think Pythagorean theorem might be a little better. You can certainly use this, and you can say opposite over adjacent, and we could use, let's say, tan in this case, or toa. But we'd have to make sure that we're using, I think, more than 10.5. You'd probably want to go back to the calculator and write a few more digits just to make sure you get the full accuracy. If we just use Pythagorean, then we'll make sure that we have all accuracy. So that's what I'm going to do here. So once again, here is a right angle triangle. What is a Pythagorean theorem if we have A, B, and C in a right angle triangle? Well, it's a squared plus b squared, b squared equals c squared. In this case, we know this opposite side length and the hypotenuse. So let's go ahead and map onto what we have here. So in this case, if we call this, for example, x, which I think should be okay. If we call this x, then what do we have? We have x squared plus 218 squared equals 1200 squared. And here you might think, oh, now I've got to do some complex algebra or bring this over. And you could, but we can actually just end solve this right away. So we can actually just do this and solve for this base, this distance right here. So let's go ahead and do that. So menu, algebra, numerical solve, and then what do we have? We have a squared, or in this case x squared, plus 218 squared equals 1200 squared. And we're asking the calculator to solve for this distance x. And here we have a length of 1180.03. So this is measured in meters, I think it is. So let's go back to the calculator and write this out, or sorry, the document. So x is equal to 1180, and this is already in 3 significant figures, and we are in meters, yeah. Okay, not too bad. In part C, they ask, write down your answer to part B in the form of a times 10 to the k, where a is greater than or equal to 1, less than 10, and k is an element of the integers. So integers means positive, negative, whole numbers. So what does this mean? This value a has to be between 1 and 10, and this k, this exponent, has to be a positive, negative, whole number. So essentially what they're asking is, write this value out in scientific notation. So here we are. I'm going to number this, or letter this C. Easiest way to do this, I think, is just to write out our original value, find the decimal place where it is, and then count the number of hops that you would need to create, in some sense, a number between 1 and 10. So in this case, we would need to move to the left 1, 2, 3 hops. And that's where we would put our decimal place. So now it would be a number that's 1.18. But of course, that's not it. We've done the first part of creating a number between 1 and 10. But what do these 3 hops, I guess, mean in some sense? What do they signify? Well, our base 10 system says that we're essentially moving the decimal place 1, 2, 3 hops to the right, or 10 times 10 times 10. Or we could say 1,000 times. We've made this number, in some sense, 1,000 times smaller. So in order to bring it back to what it was before, we would need to, well, multiply by 1,000 once again. 10 to the 3 is itself 10 times 10 times 10, or 1 with 3 zeros, just 1,000. So essentially, another way of writing 1,180 is 1.18 times, well, in this case, 1,000, or 10 to the 3. So now we've written it in scientific notation. I think the easiest way, once again, find the decimal place, count the number of hops. We've created a decimal between 1 and 10, and then the number of hops correspond to, in this case, the exponent that we'd like to, I guess, raise the power of 10 to. Okay, let's go on. Question 2. In the first month of a reforestation program, the town of Nirim plants 85 trees. Each subsequent month, the number of trees planted will increase by an additional 30 trees. The number of trees to be planted in each month of the first 3 months are shown in the following table. So we have month 1, 2, 3, and then the number of trees planted within that month. Find the number of trees to be planted in the 15th month. Okay, so this is a 3-mark question, not insignificant, so there's going to be some process. A few different ways that we could do this. First off, we see this as an arithmetic sequence. Arithmetic sequence means, once again, we're adding or subtracting to go from one term to the next. Here they already tell us that we add by 30 to go from one term to the next. In terms of arithmetic sequence, we would call this our common ratio. So the common ratio is itself 30, the value that we add or subtract to go from one term to the next. And you might say, okay, 15, we're already at 3, so I just need to add 30 again. And you could write this out as 145 plus another 30, plus another 30, plus another 30. And you would eventually get to the 15th month. To be honest, I think in terms of the overall marks, you might actually only get 2 out of the 3. I think they're probably expecting a more formal process in some ways. So let's use our arithmetic sequence formula for this. So once again, we can actually find this in the formula booklet, but here it is again. Un, the value of a given term, is equal to U1, value of the first term, plus n minus 1 times d. So the 2 ingredients that we need in order to find a formula for an arithmetic sequence is going to be the value of the first term, which we have, and the common difference, which we found right here. So let's go ahead and substitute, and then we can write a formula. And then the idea is we can use that formula to find the value of the 15th month. So let's go ahead and write this out. So U1, value of the first term, is equal to 85. N minus 1, n is just a term number, it's interchangeable. We put it in when we want to find, let's say, the output of some input, and our input is n. Common difference is 30. Okay, so we can expand this if we want, but we can actually just leave it like this, and this is our general term. This allows us to find any value within an arithmetic sequence, so the value of any term within an arithmetic sequence. In this case, we want to find the 15th month, or the value when n is equal to 15. So what is U15? So let's go ahead, wherever we see n, let's replace it with 15, and this will be what we use to find the 15th term. So 85 plus, in this case, n is equal to 15. 15 minus 1 times 30. So we can actually work this out, but let's go to the calculator and solve for this. Okay. So 85 plus 15 minus 1 times our common difference of 30. This looks good. And we'll have 505. So this is the number of trees planted in the 15th month. So let's write this out. In this case, we have 505, and I guess our units are trees. We can write this. It's 505 trees. Okay. Good. Let's go on to question B. Find the total number of trees to be planted in the first 15 months. Okay. So, nice question. Keyword here is total. So we're still dealing with arithmetic sequences, or with an arithmetic sequence, but in this case we want to find the total or the sum of all trees. So we know how many trees were planted in the first, second, third. We know it grows predictably. What are the total number of trees that were planted? So for this, let's use our sum formula. So remember, we have two different sum formulas. The first one is Sn, the sum of n terms, is equal to n over 2, and it's u1, u1 plus un. Our second formula, they're both equivalent, but sometimes one is more useful than the other, starts off the same as n over 2, and it is 2u1 plus n minus 1 times d. Both of these are given to us in the formula booklet. Sometimes it's going to be easier to use one formula or the other. So it depends. They both have this n over 2, but if we look at the variables, this one has first term and last term. So if we know the first term, the value of the first term, we know the last term, the value of the last term, and the total number of terms, this one's going to be easier. If we don't know all of these things, then we're going to need to use this one. So in this case, we don't actually know the value of the 15th term. Well, we do actually. We do know the value of the 15th term. So in this case, we can actually go ahead and use this one. If we didn't, we could just use this formula right here, which just has u1, n, the number of terms, and then the common difference. Both of them will work okay, but since we already know the 15th term, this one might actually be a little quicker. So let's go ahead and substitute. So Sn, in this case n, is equal to 15. The total number of the 15th terms summed together. N is equal to 15 over 2. U1 was the value of the first term, which is 81, and the value of Un, or the value of U15, is equal to 505. So let's go ahead and work that out on the calculator. So we have 15 over 2 multiplied by 81. Sorry, it's not 81, it's 85. 85 plus 505. And we have 4,425 trees. So let's go ahead and write that out. So this is 4,425 trees. Okay. Go on to question C. Let me erase this and we'll write C right here. In part C, we're asked to find the mean number of trees planted per month during the first 15 months. Okay, so kind of an interesting question here. What is the mean? What is x bar? X bar is sum of all values over, we can say, the number of values. So in this case, it would be number of trees planted. Actually, this would be the total number of trees planted over total number of months. So we could say, okay, we planted 85 plus another 115 plus another 145. But we know actually altogether there were 4,425 trees that were planted. So overall, 4,425 trees planted. And the question is, how long did that take us? Well, in this case, 15 months. So overall, if we planted 4,425 trees over 15 months, this would give us our average, I guess, rate, you could say, of how many we planted per month. So working that out on the calculator here, 4,425 over 15, this would give us 295. So on average, we have planted 295 trees per month. So sum of all values, once again, total number of trees planted over, well, total number of months it's taken, and then we can find 295 trees per month. That's our average. All right. Question 3. Devon throws a javelin in a school track and field competition. The height h of the front tip of the javelin above the ground in meters is modeled by the following quadratic function. H of t equals negative 3.6 t squared plus 10.8 t plus 1.8, where t is greater than or equal to 0. T is the time in seconds after the javelin is thrown. Part A, write down the height of the front tip of the javelin at the time it is thrown. So this is kind of a classic input-output question. We have some function which relates time to height, and often, fairly often at least, they ask us to find some initial starting value. We also see these with exponential functions and so on. So in this case, the time at which it is thrown, in this case, t represents the time in seconds after the javelin is thrown. So the time at which it's thrown would be the moment, the instantaneous moment where it leaves this person's hand, or in other words, that's when t itself is equal to 0. So for part A, what is the value of h when t is equal to 0? So let's substitute t equals 0 into our function right here, and then we should be able to find the value. So h of 0 is equal to negative 3.6 t, 0 squared plus 10.8 times 0 plus 1.8. On a timed exam, you might actually just say, hey, I know everything multiplied by 0 itself goes to 0, so these terms will just disappear, and you'll just be left with this constant of 1.8. And that would be perfectly acceptable as well. It's just a 1-mark question, so they're just looking for the answer of 1.8 meters. All right. Part B. Find the value of t when the front tip of the javelin reaches its maximum height. Okay, not a bad question. A few different ways we could solve this. We could actually solve this with calculus. We could solve this using vertex formula, so writing negative b over 2a, knowing that these coefficients in front of t are a, b, and c, and then substituting that value in to find the highest point. But I think, to be honest, the easiest way is actually just going to be to graph this and then find the highest point here. Especially since these numbers aren't that large, it doesn't seem like we'll need to really adjust the window too much. So let's go ahead and graph this and just find its highest point. So here we are. Negative 3.6, we'll need to use x because that's what our variable is in terms of. Negative 3.6 x squared plus 10.8 x plus 1.8. All right, let's see if all of that is good. Looks okay. All right, I don't think we'll need to zoom out. You can just pinch zoom, pinch grab, I guess in this case. Analyze graph, maximum. And in this case, what do we have? The value of t when it reaches its maximum height is going to be 1.5. After 1.5 seconds, it reaches a maximum height of 9.9. So let's go ahead and write that out. I'm going to write it out here. B t equals 1.5. This is a 2-mark question, so likely some process being expected here. Little sketch. Quickly label axes. This is height against time. We know it intersects at 1.8, but really the critical value here is they're expecting some kind of symmetry, and then you can just label this point t of 1.5, and then the height at this point was 9.9. So make sure you get some process as well. Even if you know how to find the answer, make sure to show some process because it's a 2-mark question. All right. Part C, find the value of t when the front tip of the javelin strikes the ground. Okay, so here we have our quadratic once again. It's height against time, maps the trajectory or path of this javelin through the air, and there's going to be this point when it reaches ground. When does it reach the ground? Well, when height itself is equal to 0. 2 different ways that we could solve this. Knowing that we have some function which relates height to time, one thing that we could do is we could say, okay, well, what is t when h itself is equal to 0? We just substitute 0 in for h, and then we could find that value of t. So this would be one algebraic way to work this out. That's certainly acceptable. Just be careful. If you were to end solve this, it'd probably give you a negative value first. So just make sure you have a domain restriction and find the positive value, of course. Other way, since we already have a graph here, let's actually just go to our graph and then we'll find our intersection point for when, in this case, when h is equal to 0. So here we are, we're already in the graph. We'll go menu, analyze graph, and in this case, we want to find the 0. Here we go. So after 3.158 seconds, or to 3 significant figures, after 3.16 seconds, this javelin hits the ground. So I think that's going to be the easiest way. So let's go and write this out. T is equal to 3.158, 3 I suppose, or to 3 significant figures, 3.16 seconds. If you wanted to show process, we could simply, I'm actually going to write out another one, just because I think sometimes not wasting too much time. I think an examiner would catch this, to be honest, but writing out a solution to a question, or what I mean is showing your process to a given question within the graph of a previous question. Could it be missed? I'm not sure. I think potentially it's a danger, or at least to avoid that, simply just draw another one and show that point. So here it is, where we hit the ground. After 3.16 seconds, the height is equal to 0. Solved through graphing. Okay. Question 4. Sergio is interested in whether an adult's favorite breakfast berry depends on their income level. He obtains the following data for 341 adults and decides to carry out a chi-squared test for independence at the 10% significance level. So here we have income level and favorite berries. Part A asks us to write down the null hypothesis. This is a 1-mark question. So for chi-squared independence tests, we always have this familiar structure. We have blank this is the null hypothesis. We have blank is independent of blank. And then really it's just a matter of finding what our categories are. In this case, it would be favorite berry, or we could say berry preference. Favorite berry is independent of what? Of income level. We're essentially asking if these two categorical variables, if these variables are independent of one another or influencing. Let's just say, does income influence favorite berry? I guess we could possibly say that favorite berry influences income level. Are these two things independent or somehow influencing one another? All right. Or showing some kind of relation. I don't think we could potentially say causal mechanisms here. All right. Part B, find the value of the chi-squared statistic. Okay, so this is somewhat procedural actually. Let's just go set up a matrix and then we'll run a chi-squared test statistic. So let's go to the calculator here. We will go menu, matrix, and we'll create a matrix. Here we have a 3 by 3 matrix. So 3 by 3 matrix. And let's put in those values. So 21, 39, 32. 39, 67, 45, 30, 42, 26. All right, I'm just going to check these over just to make sure. 21, 39, 32. Looks good. Looks good. All right, now it's all define our matrix. So Control var, and usually define it as A, but it doesn't really matter. All right, now let's run our stat test. So statistics. In this case, we want to run a statistical test, and we want to run a chi-squared two-way test. All right. Observed matrix, we defined as A. And here we go. So this is our p-value, our degrees of freedom. So in this case, they wanted us to find the chi-squared statistic. So here it is, 2.268. So let's go back to the document and write that up. So chi-squared is equal to 2.268, or we could say 2.27 to 3 sig figs. All right, 2.27. The critical value of this chi-squared test is 7.78. Part C asks us to write down Sergio's conclusion to the test in context and justify your answer. All right, so 2-mark question. Structure of these is often the same. Often we can compare the p-value with the significance level or the critical value, or since they give us a chi-squared value here, we can compare our chi-squared value with the chi-squared critical value. We're not forced into either direction. Just because they give us the chi-squared value here doesn't mean that we can't use the p-value that we found as well to compare against our critical level. So in this case, let's use the chi-squared critical value because it's what's given here, but we can also use the p-value all the same. So here we are, part C. Let's compare our chi-squared value with chi-squared crit. So our chi-squared critical value is 7.78, and our chi-squared value that we found was 2.27. Our chi-squared value is greater than our chi-squared critical value is greater than the one that we found. So what does that mean? The chi-squared value is a measure of difference between observed and expected values. So just based on proportions and probability alone, we would be able to write some expected values within each of these cells. When we go out and we make some observations, what we can do is we can calculate the difference between what we observe, and what we would see just based on chance alone. And if there's a big difference between what we observe and what we would expect just based on probability and chance and equal proportions, then it tells us that maybe there's something going on here. maybe these variables are influencing each other. So in this case, the difference is rather low, or at least lower than what we're willing to tolerate. So in this case, difference between observed and expected, our chi-squared value, is 2.27. And that's a lot lower than what we're willing to tolerate. Anything above this, we would say, hey, that's a significant amount of difference. Maybe there is some kind of influence because our observations are quite different than what we would expect just based on chance alone. So in this case, if we are looking at the chi-squared value, comparing it to the chi-squared critical value, difference between observed and expected isn't actually all that great. So in this case, we would accept the null hypothesis, or we could say we fail to reject the null hypothesis. Now, to use p-values and p-crit to draw out this comparison, which we certainly could, we can first find our p-crit, which is 10%, or 0.10, 10%, and compare this to the p-value that we found. And so here it is. We see that it's 0.687 to 3 sig figs. So 0.687 or 68.7%. And here we see our p-value is actually greater than p-crit. So what does a p-value measure? It measures the probability that we see these kind of results just based on chance alone. So here, in kind of plain language, I guess, we see these values 68.7% of the time, or the probability of seeing these values is 68.7%, which isn't particularly unusual. Just based on chance alone, we're going to see these results fairly often, which leads us to believe that these probably aren't influencing one another, because just based on randomness, we're going to see these results fairly often. So if p is high, we accept the null hypothesis, or once again, we fail to reject the null hypothesis. So although sometimes this is confusing because chi-squared and chi-squared, they're different in terms of if the chi-squared critical value is above or below, it's different for the p-value being above or below. But conceptually, probability that we see these results just based on chance. P is high, not particularly convincing that there's some kind of relationship. Chi-squared value is the difference, the measured difference between what we observe and what we expect. Small difference between what we observe and what we would expect just based on chance and equal proportions, probably not influencing each other either, because, well, we expect to see these kind of results just based on randomness alone. So in both cases, we accept the status quo, null hypothesis, and that's us stating that favorite berry is independent of income level. Question 5. Celeste heated a cup of coffee and then let it cool to room temperature. Celeste found the coffee's temperature T measured in degrees Celsius could be modeled by the following function. T of T equals 71e raised to the power of negative 0.0514 T plus 23, where T is greater than 0. T is the time in minutes after the coffee started to cool. Part A asks us to find the coffee's temperature 16 minutes after it started to cool. All right, so in this case, we have, again, a kind of input-output situation with exponential functions. So in this case, we input some value of time, and then it will tell us the temperature at that corresponding time. So in this case, we want to know the coffee's temperature 16 minutes after it started to cool. Or essentially, what is T for T equals 16? So we have our input, now we just need to find the output. So let's go and write this out. Here's A. We want to find T of 16, that is to say the temperature at 16 minutes. So we have 71 e to the negative 0.0514, and then once again T is equal to 16, then we say plus 23. All right, 2-mark question, you'll probably want to show the input right here, and then now we'll find our result. So let's go to the calculator here. Now we have 71 times E. So here's E right here. Oops, this is ln. There we go. E to the negative 0.514. and multiplied by 16 plus 23. Okay, let's go ahead. And our answer is 54.1957 or 54.2 degrees to 3 sig figs. All right. So writing that out, 54.2 degrees. Okay, let's go on. The graph of t has a horizontal asymptote. Part B asks us to write down the equation of the horizontal asymptote. All right. So first off, what is a horizontal asymptote? So horizontal, as the name suggests, is left-right. This horizontal or parallel with the ground in some sense. And our asymptote is a line, or I think we can say line, a line that we approach, a value that we approach, but never entirely reach. So in this case, here's our temperature as a function of time. And we can say what happens when you leave a cup of tea or a cup of coffee out in room temperature. Well, what happens is it gets cooler if the temperature within the room is colder than the coffee. And it doesn't happen all at once, but gradually. And then it approaches room temperature. So it approaches room temperature, and this value, this would be our horizontal asymptote. The value that we approach, but never reach. If I can move this down, I think that looks good. So in this case, when they ask us to find the horizontal asymptote, they're asking us to find the value that this temperature approaches, but never reaches. And we can also have vertical asymptotes, but here we're asked about the equation of a horizontal asymptote. So in this case, what is the temperature that this function, or this coffee, approaches, but never quite reaches, I suppose, at least in theory? Well, looking at this, we have this element of this function, this first term, 71e to the negative 0.0514, and then we also have this constant here. Since this is raised to a negative, it's essentially like it's being divided by e. So in this case, what can we say? If we have some value and it's being divided by an increasingly larger value, eventually it's going to disappear. It's like we're taking some value and breaking it up into an infinite number of pieces. Eventually those pieces become so small that they're insignificant. So essentially what happens, as t gets very, very big, this term itself, let me get back into a normal writing utensil. There we are. This term will itself go to 0. And all we're going to be left with is this value, this constant right here of 23. So our horizontal asymptote, what is the value that we approach but never reach? Well, that's going to be when T, the temperature, is equal to 23 degrees Celsius. So we can also just say when T is equal to 23. Remember, it's an equation, so they're expecting an equal sign, just like we would have, for example, y is equal to 5, being, well, this horizontal value right here, for example. So, once again, I hope that wasn't too long-winded for a 1-mark question. Horizontal asymptote, the line we approach but never reach. In this case, we have some function where the first term gets increasingly small as t increases, to the point where it eventually goes away. This 23 isn't impacted, it's just hanging off at the end, and it isn't influenced by what's going on here. So after this goes to 0, all we're left is with this 23, and that is the value that we approach but never reach. This doesn't go away entirely, there's always something left, at least in theory. Okay. Part C, write down the room temperature. Okay. So, this is kind of a common question, actually, or at least common structure. Often in a good IB question, they'll have one question lead into another. So in this case, horizontal asymptote, what we approach but never reach, that is itself the room temperature. So in this case, T is equal to 23 degrees Celsius. Part D. Given that T inverse of 50 is equal to K, find the value of K. All right. So 2-mark question. Oftentimes students might be a little unfamiliar with inverse or intimidated by inverse, but it's not too bad. So with a function, we have inputs and outputs. Normally, for example, in this case, we have our input of 16, and then we found the output for our temperature. What an inverse does, it switches inputs and outputs. So here, this t inverse 50, all we're essentially asking is the output is 50, what was the input? So thing to remember, inverse switches inputs and outputs. Normally, we have an input into our normal function, so we replace it, t, for example, with 16, and then we find the output. Inverse reverses that. What's within here is actually our output. So output is equal to 50. What was our input? So in this case, let's write out our problem for d. And here's our function right up here. Essentially, if our output was 50, what was our input? Or in just maybe more kind of commonplace language, if the temperature itself was equal to 50, what is the time in which that occurred? So we want to solve for t right here. All right. So we've got some equations set up with just one unknown. Let's go into the calculator and end solve. So menu, algebra, numerical solve. Output is equal to 50. What is the input that makes that true? 0.0514t plus 23. And we want to solve for t. Okay. There we go. After 18.81 minutes, we have a temperature equal to 50. So let's go ahead and write that out. T equals 18.8 minutes. I should actually say one thing that I kind of left out actually at the beginning. There's one part that might be confusing for some, and that's this idea of e. You can say, hey, isn't this a variable? Like, what do we do if we have two variables here? E is a special number in the same way that pi is approximately equal to 3.14. We have e, which is a special number, which is approximately equal to 2.72. So it's a mathematical constant. It has a lot to do with growth rates or decay rates, and it's not itself a variable. It's just such a useful and, I guess, yeah, a useful and powerful kind of constant within mathematics that we've given it its own letter in some sense. It's also what's called a transcendental number, so it goes on and on and on for infinity. So instead of saying, hey, let's always just write e to 20 decimal places, we just put e in, and we imagine that it has the full range of accuracy. So pi, special number, e, special number, not a variable, t is the only variable here. Question 6. Manny and Annabelle, mathematics teachers at Burnham High School, give their students the same examination. A random sample of the examination scores were collected from each of their classes. So here's the examination score from Manny's class and from Annabelle's class. Annabelle uses these scores to conduct a two-tailed t-test to compare the means of the two classes at the 5% level of significance. It is assumed the examination scores for both classes have the same variance and are normally distributed. The null hypothesis is mu1 equals mu2, where mu1 is the mean examination score from Manny's class, and mu2 is the mean examination score from Annabelle's class. Write down the alternative hypothesis. All right, so we've got a t-test here. We're comparing the means or the averages of these two classes in this case. And our null hypothesis is always status quo, that there's no difference, that mu1 is equal to mu2. Alternative can be of one of three forms. So we can either have mu1 is greater than mu2, mu1 is less than mu2, or it's just the case that mu1 is not the same as, it's different than mu2. Here, we don't actually, it's not stated that Annabelle wants to find out if Manny's is greater or less. We just want to find out if they're different. And different would mean not equal to one another. So in this case, the alternative hypothesis, what we would like to know is simply if they're different. That is to say, if mu1 does not equal mu2. Okay. Part B. Find the p-value for this test. give your answer correct to 5 decimal places. So this is important. Sometimes it's, I guess, an unfortunate way to lose marks just because they're asking for a specific degree of accuracy. So let's go ahead and run a t-test here. So let's go into spreadsheets. So here we are. We can call this maybe Manny and A for Annabelle, and then we can just put in these values. So 76, 77, 82, and so on. 4, 88, 90, 91, 98. And then the same for Annabelle's class. 68, 79, 81, 89, 91, 92, 92, 95. I'm just going to check these. I think it's sometimes a good idea just because it would be an unfortunate way to lose marks going through these on a test as well. 90, 91, 98, and then just really quick here, 79, 81, 89. Okay, let's run a t-test. Let's go menu, statistics. We want to do a statistical test. And in this case, we want to run a, oops, sorry, disappeared. We have a 2-sample t-test. Okay, I'm going to try once more. I think it's just the way this is being clicked. Okay, so actually it's because I'm hovered here, I think. I need to be hovered within our data entry, I guess, space. So statistics, stat tests, 2-sample t-test, and there we go. Okay, so list 1 is in A, list 2 is in M, and our null hypothesis is just that they're different. And then always we want to set this as pooled equals to yes. This has something to do with equal variance and normally distributed samples. So, okay, let's go ahead. So here we are. We are asked to find the p-value for this, and it's actually very, very high. So it's 0.9765. So let's write this out on the examination document. P-value is equal to 0.9765, or we can say 0.977 to 3 sig figs. All right. Annabelle concludes there is insufficient evidence to reject the null hypothesis. State whether Annabelle's conclusion is correct. Give a reason for your answer. Okay. So in this case, once again, we want to compare the p-value to p-crit, or the significance level here. So let's set up some comparison right here. I think it's a little strange that they ask us to essentially, again, compare p-value and critical value on the same test, but here we are all the same. So 0.977, and as a percentage, this is 97.7%. Here our significance level is just given as 5%, and I guess we could wind this back if we wanted. So what are we saying? P-value is higher than p-crit. That means we're going to see these kind of results 97.7% of the time. This is the probability we're going to see these results. And it's not particularly convincing to say that there's some kind of difference, because just based on randomness alone, we go to any two classes and look at their examination scores. Well, the probability that we're going to see this kind of difference in the means is, well, not too convincing here. It's not too unlikely that we're going to see these results just based on chance alone. So in this case, we would accept the null hypothesis or fail to reject. And that's what Annabelle is saying, that there's insufficient evidence to reject the null hypothesis. So in this case, whether Annabelle's conclusion is correct, we could say that Annabelle is correct. Annabelle is correct. We fail to reject the null hypothesis. All right. Question 7. on the 1st of December 2022, Laviola invests €800 into a savings account which pays a nominal annual interest rate of 7.5% compounded monthly. At the end of each month, Laviola deposits an additional €500 into the savings account. At the end of K months, Laviola will have saved enough money to withdraw €10,000. Question A asks us to find the smallest possible value of K, for K is an element of the positive integers. Integers, remember, are positive, negative whole numbers. This little positive says we're just talking about positive whole numbers, so counting numbers, 1, 2, 3, 4, 5. No fractions, no decimals, positive numbers, whole numbers. Okay, so we've got a financial solver question, or a financial mathematics question. How do we know what process we should use? We're depositing some amount of money and it's being compounded. So you might think, hey, can we use the compound interest formula? But since we're making payments, incremental payments at the end of each month, as soon as we begin to add or, let's say, take away from an account incrementally through time, then we need to use our financial solver. We can use the compound interest formula when we just deposit money into an account, let it stay there, and then just grow interest. The moment we start to add incrementally to this account or withdraw, let's say, little pieces out of it through time, then we need to use our financial solver because things get a little, I guess you could say, messier or complex. So I've already got our, what can we say, the different variables that we're going to need for our financial solver. Here they are. Now let's go ahead and input these values and solve for some unknown. In this case, the amount of time it will take for K. All right, so easiest one, or most straightforward one, I think is always interest, 7.5% in this case. It's compounded monthly. That means CPY, compounding periods per year, is 12. We also know she's going to make payments at the end of each month. So in this case, 12 payments per year. Let's see the final value. We know she wants €10,000 in the account at the end of K months. So final value is itself 10,000. Payments, we know she is going to deposit $500 into a savings account per month. So we would put, this is the part where we need to be careful. So PMT, money flowing out, money flowing in. We should use positive, negative to distinguish. So PMT is money flowing out. Often we say money flowing out is negative. It leaves our pocket, so we would say negative. And then the present value, we have €800 in this account. This is the same idea. Although it is her money, it's in some ways out of her hands. It's in the bank. So we would again put this negative 800 here. And then what we want to solve for is K. We want to find the amount of time it takes. So let's leave N as our unknown. So now I think we have everything we need. Let's go ahead and solve this in our financial solver. So here we are. Interest rate is 7.5%. Present value, negative 800 payments. Monthly payments is negative 500. Final value she wants is 10,000. Payments per year is 12. Compounding period is 12, and the payments are made at the end of every month. Let's find out our value of N, that is to say how long it takes for us to reach, or in this case, Laviola to reach €10,000. In this case, it will take 17.307 or 17.3 months. So let's go back to the document and try to unpack this a little more. So in this case, N is equal to 17.307. But here, they're asking us, okay, K has to be a positive integer. That means whole number. So in this case, let's say 17 months have passed. Laviola checks her account. It's not quite 10,000. She's not going to be able to check her account, let's say 10 days in, that is to say 30% of the way through the month, and see, okay, now I have 10,000, because her interest rate is 7.5%, but it's compounded monthly. That is to say, it's paid out at the end of a month. So it's not going to be until the 18th month that she actually has her $10,000. She'll have slightly more than 10,000 at that point. So it's not like she can check 10 days in and say, hey, I've made it. It's not going to be until the end of, well, in this case, the 17th month or right at the beginning of the 18th month that she'll have this money in her account. So in this case, K, oops, I don't need that color. K, either that. K is equal to 18. So after 18 months, she'll have 10,000 euros. All right, part B. For this value of K, find the interest earned in the savings account. Express your answer correct to the nearest euro. Okay, so 3-mark question. Not too bad of a question. So what do we know? At the end of 18 months, we'll actually have to put this back in and find the total amount, because for this value of K, she's going to have slightly more than $10,000 or 10,000 euros. But when we put this value in for K, that is to say 18 in here, she's going to have slightly more than 10,000. And her total amount is itself, let me write this out here, the total amount that she'll have in this account will be made up of that initial deposit, her initial deposit. It'll be made up of the payments that she has made, so those $500 payments that she's made, and it'll also be made up of the interest that she has earned. So I'm actually going to move this down just so it's fully, I guess we can see it in one line. So the total amount, whatever it is after 18 months, will be made up of that original $800 that she put in, 18 months worth of $500 payments, and then the amount of interest that the bank has paid her over this amount of time, over these 18 months. So we know 3 out of these 4 things. Let's find the interest. Okay, first let's go back to our calculator and write in a value of 18 for K. So 18 months, and then we'll replace this final value right here. So everything else is the same. 7.5% interest, initial deposit, $500 payments, and so on. So let's find the final value at that time. So she has $10,389.39. So let's write that out as our total after 18 months. So here we go. $10,000, 389.39 cents. The initial deposit was itself 800. The payments that she made 500 payments over, what can we say? I'm just wondering, is it over 17 months or 18 months? So think about this. So N, payments per year is equal to 12. N in this case is, this would be 18 months of payments. So I believe she has made 18 months of payments, because N itself, N and PPY are linked together. Payments per year is equal to 12. How many payments? N is equal to, well, in this case, 18 payments. Then the last little bit is interest. Once again, total amount that she has in the account is equal to how much she put in at the beginning, how much she contributed, and then of course the bank contributed some in terms of interest as well. And that's what we want to find out, how much interest she has earned. So let's go to the calculator and work this out, just in terms of, could we end solve this? We can end solve this, but we can also work it out algebraically. Let's end solve this. I think it'll be all the same. Menu, algebra, numerical solve. This is our final amount, 10,389.39, and it equals to that initial deposit plus 18 payments of 500 plus some interest amount. We can put it as X, and we want to find out what that missing value is. So in this case, she has earned $589.39 in interest. So let's write that out. Interest is equal to $589.39. Of course, to work this out, we could have just taken this final amount subtracted 800, and then found this and also subtracted, and we could have said what is left. We could have worked this out algebraically as well, but there it is once again. And let's write our unit as in euros. Okay, so let's go on. Did it ask us to, okay, so it's asking us to write this in the nearest euro. So in this case, it's only 589 euros. Okay. Question 8. Roy is a member of a motorsport club and regularly drives around the Port Campbell racetrack. The times he takes to complete a lap are normally distributed with a mean 59 seconds and standard deviation of 3 seconds. Part A asks us to find the probability that Roy completes a lap in less than 55 seconds. So keyword here, normally distributed, tells us we're dealing with normal distributions. And I think for a lot of these problems, I think it's not a bad idea to sketch these situations. First, because they can be used as process, and then they also help us see what's going on. So in this case, Roy completes a bunch of laps. His performance is not, 100% consistent. His results are normally distributed. So normal distribution centered about a mean, in this case, a mean of 59 seconds, and then standard deviation, which is a measure of spread, is 3 seconds. Okay, so let's see what they're asking us to do here. We want to find the probability that Roy completes a lap in less than 55 seconds. So on average, he's going to complete a lap in 59 seconds. So what is the chance that he completes a lap in less than 55 seconds? So here's 55 seconds. Maybe something like this. Area under the curve represents, all of the theoretical laps that I suppose Roy could make. We want to find the probability for the area under the curve that is, less than for 55 seconds. So once again, standard normal curve centered at a mean of 59. This is the average time it takes for Roy to complete a lap. What's the probability that he completes a lap in under 55 seconds? That is to say, what is the percentage of the error under the curve to the left of 55? Let's go ahead and work this out with normal distributions. So menu, probability, distributions, and in this case we want to go normal CDF. Our lower bound we can keep as this super small negative number, but we want to go all the way to 55 seconds. Our mean is itself 59, and our standard deviation is 3. Oops. So remember, once again, you could, in practice, use 0 here. We just want to make sure that we sweep out all the area from the left all the way up to 55. So in practice, you could use 0, and that would make sense, actually, in the context of this question, because you can't complete a lap in negative minutes. But all the same, just make sure you choose a number that's small enough to capture everything to the left of this 55, this upper bound. All right. So what is the chance that he completes a lap in under 55 seconds? Probability is 0.0912, or 9.12%. So let's go back to the document and write this out. This is one of those areas where the IB actually accepts calculator notation. So we can write norm CDF, and then we can write, I'm going to write actually 0 here, but you can write -9 times 10 to the 9999. So, but lower bound, upper bound, mean, standard deviation, and in this case 0.0912, or as a percentage we could say 9.12%. Okay. Roy will complete a 20-lap race. It is expected that 8.6 of the laps will take more than t seconds. Part B asks us to find the value of t. So this question is actually not too different than the first question, but it's a little more conceptual, and we kind of have to dig a little, I suppose, in some ways to find out what it is they're actually asking us to do. So Roy's going to complete 20 laps, and 8.6 of the laps will take more than t seconds. So we do have some kind of ratio or fraction. We know that 8.6 out of the 20 laps are going to take longer than a certain amount of time. So let's actually just work that out. 8.6 divided by 20. As a percentage, I guess first as a decimal we could say, this is equal to 0.43, or if we wanted to, we could say 43%. And now if we rephrase this question, and we say that 43% of the laps will take longer than t seconds, this question becomes, in some sense, more manageable. So 8.6 of the 20 laps will take more than t seconds. 43% of his laps will be longer than, well, what is the value of t? So in this case, let's draw another normal distribution. I'm going to actually grab this and bring it down here because I think we'll need it. Let's write another normal distribution. So here, once again, normal distribution centered at the mean itself of 59. In this case, there are various times that a lap might take. We want 43% of the laps to be longer than some value of t. So in this case, let's write this out. We know this is the 50%, the dividing line. So we'll put some value here of t. And we know, or we assume that, might be a little small on the diagram, but 43% are to the right of this value. So in the first case, they gave us a cutoff point, and they asked us to find the percentage under the curve. And that was norm CDF. Here, we have the percentage, and we're asked to find the cutoff point. So in this case, 8.6 of the 20 laps take longer than some value of t. 43% take some longer value than t. And we need to find, well, what is this cutoff point? Okay, so let's go in. We'll run inverse normal here. And there's one final thing to be mindful of, but I'll show you that once we get to the calculator screen itself. Okay, so let's go menu, probability, distributions. Here we want to go inverse normal. So here we go, the area. So going back to our document just for a sec. By convention, the calculator sweeps area from left to right. So if you want to reach this value of t, what is the area that you need to sweep through? It's not 43% because that'll only take you to about here. The area that we need to sweep through will be equal to, well, if there's 43% on the other side, that means we need to sweep through, well, 100 minus 43. This will be equal to an area of 0.57 or 57%. So going back to the calculator here, sweeping left to right, if we want to reach 43%, we've got to sweep through an area of 57%. Mean, once again, is 59. Standard deviation is equal to 3. Let's find that cutoff point. In this case, it is 59.529 or 59.5 seconds. So let's write that out. T is equal to 59.5 seconds. And that should be reassuring. 59 is the mean. 50% is here, 50% is here. If it's just slightly over on this side, this is, a reasonable assessment or reasonable value in terms of, 43%. 43% would be to the right of this. All right. So on an exam, this would be fine for process. If you wanted to, you could also write calculator notation as well. Inverse norm. And then you can say sweep through an area of 0.57, mean, standard deviation, and then you can put the answer as 59.5 seconds. Okay. Question 9. Taizo plays a game where he throws one ball at two bottles that are sitting on a table. The probability of knocking over bottles in any given game is shown in the following table. So 50% chance of knocking over 0 bottles, 40% of knocking over 1, and 10% of knocking over 2 bottles. Taizo plays two games that are independent of each other. Find the probability that Taizo knocks over a total of 2 bottles. So we have a 4-mark question here. I think that's important because it tells us in some ways the level of complexity of this problem. So it might not be as straightforward as it might seem on the face of it, I suppose. So let's ask the question, how can we knock over 2 bottles after 2 games? Well, we could knock over 1 on the first game and then 1 on the second. We could also knock over 0 on the first game and, 2 bottles on the second. But there's one case that if we're considering all possible outcomes, there's also the case where we could knock over 2 bottles on the first round and then 0 bottles on the second round. And that would also count in terms of the total set of possible outcomes. So one way to actually visualize this is to draw a tree diagram. So let's draw a tree diagram, and there's not too many events here, so we can show every possible event or everything that could happen. So initially we have these 3 events, right? 1, 2, 3. I hope that's okay. Okay. So this is either going to be 0, 1, or 2 bottles. And the probability for each is 0.5, 0.4, and 0.1. And of course, all these probabilities sum to 1. And then on the second row, once again, there's a probability of, I don't know if I'm going to have enough room here, but we're going to have 0, 1, or 2 bottles. I'm going to try something maybe too clever. That's okay, not bad. Again, we can knock over on our second trial 0, 1, or 2 bottles. And then lastly, once again, we can knock over 0, 1, or 2 bottles. And these are all the possible things that can happen. You could have maybe poor luck and, knock over 0 bottles altogether, or 0 and then 1. What we're interested in is finding the probability that he knocks over a total of 2 bottles. So how does that occur? Well, he can knock over 0 bottles and then these 2 right here. So I'm actually going to write probability for each once again. Hopefully this won't take too long. I suppose I could have copy-pasted even this section, but that's fine. Okay, 0.1, and then once more here. Probability of 0, probability of 1, and then probability of 2. Okay, so here's one way in which he can knock over 2 bottles. 0.5, 0 bottles, and then 2 bottles. Multiplying along the branches, since these are themselves independent events, we can find the probability of this outcome. Knocking over 0, and then knocking over 2. And that would be equal to 0.5 times 0.1. That would be this event right here. What is the other way? Well, he can also knock over 1 bottle and then knock over another bottle. That would be 0.4 times 0.4. And what about this final way? Well, he could knock over 2 bottles and then knock over 0 bottles. In this case, that would be 0.1 times 0.5. There are 9 total possible outcomes. So 0, 0, 0, 1, 0, 2, and so on. What is the probability that he can knock over 2 bottles? All of these outcomes must sum to equal 1. These are the only outcomes that match our final description of knocking over 2 bottles. So what is the probability of knocking over 2 bottles? Well, the sum of outcomes that match this, criterion, or this final result of knocking over 2 bottles. So let's go ahead and work this out. This would be equal to 0.05. This is 0.16, and this is once again 0.05. Altogether, I'm going to actually add like this. I hope that's okay. And this will give us 0.26, or we could say 26%. So, what is the probability of knocking over 2 bottles? In this case, it would be 26%. Okay. I'm not sure if I should provide any more explanation here. I think that's potentially okay. Once again, this tree diagram represents the total set of possible outcomes. So we can't just say 0 and 2 and multiply, because technically we can also have, on another game, 2 bottles and then 0. Total set of possible outcomes, which ones conform or match our desired outcome? Well, here we get 2 points, here we get 2 points, here we get 2 points, and then this sums to 26% of our total, I guess, what can we say? 26% of all possible, not all possible outcomes, but the final probability is 26%. In any given game, Taizo will win K points if he knocks over 2 bottles, win 4 points if he knocks over 1 bottle, and lose 8 points if no bottles are knocked over. Part B asks us to find the value of K such that the game is fair. So if a game is fair, we have expected return equal to 0. Another way we could say that is winnings balance out losses. So in this case, what is the expected return? We can find that there's going to be this unknown K, but we know that its result, that is to say the expected return, should equal 0. So let's go write an equation for expected return, and then we can set it equal to 0, and I think that should be a good way to solve this. So expected return is something like a weighted average. So we have a probability of knocking over 2 bottles, and this is equal to 0.1, or I guess we could say 10%. 10% chance of winning K points. So let's write that out. This is 0.1 chance, not 0.1 chance, but a 10% probability of winning K points. Plus, we have this 40% chance, or 0.4, probability of 0.4 of winning 4 points. And that's if we knock over 1 bottle. So in this case, 0.4, 40% chance of winning 4 points. And then lastly, we'll lose 8 points if no bottles are knocked over. And that would be a 50% chance. Or we could say half of the time we will lose 8 points. Fair game is when expected value is equal to 0. So we'll set all this equal to 0. All right, now we've got an equation. Here we go. So this must equal 0. Equation with only one unknown. We can actually go ahead and solve this. So let's go and do that. Menu, algebra, numerical solve. So 0.1 times k plus 0.4 times 4 plus 0.5 times, I'm actually going to write this with some brackets because we have some negatives side by side. So -8. And all of this should be equal to 0. And we want to solve for k. So just make sure that this is all okay. This looks good. And so k itself must be equal to 24. So you earn 24 points for knocking over 2 balls with 1 shot. So writing this out, k is equal to 24. Once again, expected value for a fair game is equal to 0. You can kind of read expected value as fair game. Expected value is a weighted average. 10% chance of getting K points, 40% chance of getting 4 points. To counteract this 50% chance of losing 8 points, and we have such a small probability of winning K, K has to be significantly larger in order to balance this out and make sure it equals 0. Question 10. Stars are classified by their brightness. The brightest stars in the sky have a magnitude of 1. The magnitude m of another star can be modeled as a function of its brightness b relative to a star of magnitude 1, as shown by the following equation. M equals 1 minus 2.5 log base 10 of b. A star called a cubans has a brightness of 0.0525. Find the magnitude of a cubans. All right, so here's our magnitude m. This is what we want to solve for. We're given the brightness of a cubans as 0.0525, and essentially what we have here is this logarithmic function, and just like a lot of our function questions, we have inputs and outputs. In this case, we put some value in for b, input of brightness, and then we can find the corresponding magnitude. So although we're dealing with log, and log isn't a variable, it's a function like sine, cos, tan, for example, we still have this idea of an input and an output. So let's write this out, input this value for brightness, and then we'll find the corresponding magnitude. So magnitude is equal to 1 minus 2.5 log base 10, and our brightness in this case is 0.0525. So really not a bad question, even though it might look kind of confusing or complex with logarithms. For 2 marks, it's not a bad input-output question. So let's go work this out on the calculator. Here we go. 1 minus 2.5. Here's our log right here. Log base 10, and then of 0.0525. And the answer is 4.1996. So the magnitude of 4.1996 to 3 sig figs, this would be 4.20. Let's write this out. So m equals 1996 or 4.20. Okay. Ceres has a magnitude of 7 and is the least bright star visible without magnification. Part B asks us to find the brightness of Ceres. So again, not a bad question, especially for the 10th question in paper 1. Input-output kind of question. In this case, we know what the magnitude is. M is equal to 7. What's the corresponding brightness? So really actually not too bad of a question. Input-output question for a general kind of function, but now we're dealing with logarithms. So output m is equal to 7. What is b? So writing that out, 7 is equal to 1 minus 2.5 log base 10 of b. Now we want to find out what b is, and then we should be good. So let's go to our calculator. We'll need to use nsolve here, algebra numerical solve. 7 equals 1 minus 2.5 log base 10 of b, and ask the calculator to solve for b. In this case, brightness is 0.003981. So let's go back to the document, write that out. B is equal to 0.003981, or if we want to 3 sig figs, 398. Okay. Part C. Find how many times brighter a cubans is compared to Ceres. All right. So we know the brightness of a cubans, and we know the brightness of Ceres. So essentially we're asked to find, in some sense, a ratio. So brightness of a cubans compared to the brightness of Ceres. Let's call B as, let's write this. Brightness of a cubans over brightness of Ceres. What does that look like? Brightness of a cubans is, I'm going to actually write it underneath. 0.0525. Brightness of series is equal to 0.00398. And that's all it is, really. How many times greater is the brightness of a Kubans compared to the brightness of series? So let's go ahead and put this into the calculator, and we should be able to find a result here. So here we go. Setting up a fraction. 0.0525. And then here's the brightness of series, 0.00398. I'm going to use full sig figs as 3981. Okay, so it is roughly 13.1876, or 13.2 times as bright. Let's write that out. 13.2 times, we can say. All right, so not too bad of a question. Sometimes logarithms might seem a little intimidating, but it's not too bad, especially sometimes the general form is kind of like input, output in various kind of structures. All right. Question 11. Christie's house is located on a long straight road which traverses east-west. The road can be modeled by the equation y equals 0, and her home is located at the origin 0, 0. She is training for a marathon by running from her home to a point on the road and then returning to her home by bus. The first day, Christy runs 2 kilometers east to point A, 20. The second day, Christy runs west to point B. The third day, Christy runs 4.5 kilometers east to point C, 4.50. The information is represented in the following diagram. Each day, Christy increases the distance she runs. The point she reaches each day can be represented by an x-coordinate. These x-coordinates form a geometric sequence. Part A asks us to show that the common ratio r is negative 1.5. All right, so some key information here. They tell us that this is a geometric sequence, and then they're asking us to find, or actually just show that the common ratio is equal to negative 1.5. So geometric sequence, I suppose what we could ask ourselves in this case is, how would we find the common ratio if we knew that it wasn't just simply positive, positive, and more positive, but also that it, fluctuated from positive to negative to positive. So geometric sequence, we multiply by some value to go from one term to the next. In this case, it's negative 1.5. If we didn't know it was negative 1.5, how could we find it? So 2 different ways. One is we could use the geometric sequence formula. Un is equal to u1 times r n minus 1. Substitute known values, and then we could solve that way. But I think for some of these, conceptually, it's kind of nice. I think often drawing out tables is actually quite good, quite beneficial in terms of seeing what's going on. So let's draw this out. N, term number, or in this case, the number of days, or day number rather. And let's say this is d, the distance that she travels. On day 1, she travels 2 kilometers, east in this case. So here we have east representing the positive and then west representing negative. We don't have to worry about the y coordinates because we're always on this line. Y is equal to 0. So essentially this d is just the distance, in this case, distance along the x-axis that we travel, and it's directional. So day 2, we don't actually know. It's some value b, but we can leave this empty for now. And day 3, she travels 4.5. So I often like this method just because although it doesn't look like it, we actually have the kind of beginnings of some kind of equation. So let's look at this relationship. We know it's a geometric sequence. We multiply to go from one term to the next. We multiply by this common ratio of r. So here is our first day. We travel 2 kilometers. Multiplied by some common ratio, that will give us the value of, well, our second term. And then whatever our second term is, we can once again multiply by our common ratio, and that will give us the value of our third term. That's exactly what we do when we have a geometric sequence. We multiply by some common ratio to go from one term to the next. And then although it doesn't look like it here on this side, there actually is an equation. I'm going to write it out. I'm going to move this up and then write it out here, I suppose. So Doesn't look like it, but we do have an equation right here. So what do we know? We know that 2 times r should equal 4.5. And just have a look and see if you agree, I suppose. So whatever our value is for some term, multiply by r, that takes us to the third term. So 2 times r, and then we multiply that again by r, and then it should equal our value of our third term. It's 4.5. And now we have an equation just in terms of r, so we can go ahead and we can actually end solve this essentially. So 2 times r is equal to 4.5. If we were to just, I guess, rearrange this slightly, what could we have? 2 times r is 2r squared. We could already end solve this and that would be fine. 2r squared is equal to 4.5. Getting r squared all by itself, this would be 4.5 over 2. And then, of course, taking the square root of both sides, we would have a positive negative. So maybe, let's see if I can, maybe just move this over a little. I think that's okay. And then here, we have r squared is equal to 4.5 over 2. I'm going to clean it up just a little more. This is equal to 2.25. And then r, actually maybe I'll leave it like this. So what does this say? This r squared is equal to 2.25. It says some number squared is equal to 2.25. We know already that this value, this common ratio is 1.5, but it's not just 1.5, it's negative 1.5. So remember when we square a number, it could be both the positive or the negative value. So some number squared equals 2.25. 1.5 squared actually equals 2.25, but so does negative 1.5 squared. And in this case, if we want to have this movement from positive to negative to positive, this oscillation, we're going to need to have this as a negative. So in this case, r is plus minus 1.5. But if we want this back and forth, then it itself will have to be negative 1.5. All right, that's certainly one way to do it. We could use this formula as well. We know the value of u1, which is 2. Let's say we don't know our common ratio, but we do know this value here. That is to say, we know that u3, or the third term, is equal to 4.5. So when n is equal to 3, un is equal to 4.5. So essentially we know that 4.5, which is the value of u3 here, is equal to 2 times r times n minus 1, in this case n is equal to 3 at that time. 3 minus 1, and then once again we have this idea of 4 is equal to 2r squared. And then the answer, once again, r is equal to plus minus 1.5. So both ways, I think this is actually, well, we are at question 11, so I don't think it's necessarily a straightforward question. There's some algebra, but essentially what we want to do is set up some equation, and then since we have this squared term, it could be both positive or negative. So in this case, we want to choose the negative because we have this back and forth, this fluctuation between positive and negative values. All right. On the 6th day, Christy runs to point F. Find the location of point F. So I think this is actually comparatively much more straightforward and easier question than point A. So question A. So if you didn't get question A, they already give us the common ratio. We know what the first term is, so we can set up a formula, and then now we just have essentially an input-output question. So I'm going to write this out for B right here. So once again, for a geometric sequence, this is given in our formula booklet. Value of some given term, un, is equal to u1 times r. This is n minus 1. In this case, we want to find the 6th day. That is to say, when n is equal to 6, what is u6? So let's substitute what we know. u1 is equal to 2. That's the distance she travels on the first day. R, we know is, and this will be important, negative 1.5. And then n n is equal to 6. So we're raising this to the power of, might look a little funny with the brackets, 6 minus 1. And now we can go ahead and solve this in the calculator. So here we go. 2 times, I'm going to put some brackets just so we can get the negatives. Negative 1.5, and then, whoops, a little too many brackets. Raise this to the power of 6 minus 1. All right, that looks good. And we see that she travels, this I guess is to the west, negative 15.1875, or to 36 figs. This is negative 15.2. Negative 15.2. Okay. So, how far does she travel? On the 6th day, Crispy runs, find the location of point F. So we can't actually just put a value. We only know the x coordinate. So I'm going to actually write this out as negative 15.1875. But remember, this is the x coordinate. So she's all the way over here, something like that. And the x coordinate would be negative 15.1875. Let me actually make sure this is a decimal, not a comma. And the y coordinate is 0. So what is the location of point F? This is the location right here. All right, so that would be our answer, right? There we go. Negative 15.1875, and then the y coordinate is 0. You could write this to 3 sig figs as well. In part C, we're asked to find the total distance Christy runs during the first 7 days of training. So here we see this keyword, this total distance, and that tells us that we're in the realm of a sum. So a sum of a geometric sequence, this is given to us in the formula booklet, but I'll write it out here. Sn is equal to u1 times r raised to the power of n minus 1 over r minus 1. We see actually in the formula booklet it's also written like this, 1 minus rn over 1 minus r. These are equivalent formulas. It usually just depends on whether our common ratio is greater than 1 or less than 1 to allow us to avoid negatives in the denominator, for example. So it doesn't matter so much, they're both equivalent, and if you solve these with a calculator, it'll give you the same answer. In this case, since our common ratio is greater than 1 in absolute value terms, let's use this one. Okay, so sum of a geometric sequence. The danger is if we put negative 1.5 in for our common ratio right away. What that would do in this case is the positive values would cancel out the negative values would cancel out the positive values. So what this sum formula essentially would do is it would find the value of the first term, and then it would add the value of the second term, and the value of the third term, and the value of the fourth term. And it doesn't know that when we're talking about distance, we want the absolute value or just the magnitude, the total size of the distance that is traveled. If we just use this formula, positives will cancel out the negatives, negatives will cancel out the positives. And it would seem that she hadn't really traveled all that far. So what can we do in this case? We don't want the negatives to cancel out the positives. So we just imagine that r is positive. We just want the positive distances that she traveled. So instead of multiplying by negative 1.5, where we go from positive to negative to positive to negative, let's just keep r positive. And then it would be as if we were just multiplying by 1.5, 1.5, 1.5. The distance that she runs is 1.5 times as great as the previous run. And we don't actually we're not too concerned that it's just going east rather than west. So for this, we'll put r is equal to 1.5. And we'll find the value or the sum for the first 7 terms. So S7 is equal to u1 was 2, r we'll keep as 1.5, n is 6 minus 1 over, and then r once again is 1.5 minus 1. Okay, now let's go ahead and solve. So let's set up a fraction here. 2 times 1.5 raised to the 6 minus 1. Then we have 1.5 minus 1. Okay, that looks good. And total distance traveled is 41.5625 kilometers. So let's go back to the document and write this out. 41.5625, or to 3 significant figures, 41.6 kilometers. Okay, good. I think we can go on. Question 12. A cat runs inside a circular exercise wheel, making the wheel spin at a constant rate in an anti-clockwise direction. The height, h centimeters, of a fixed point P on the wheel can be modeled by h of t is equal to a sine bt plus c, where t is the time in seconds and a, b, c are positive real numbers. When t equals 0, point P is at a height of 78 centimeters. Part A asks us to write down the value of c. All right. So it tells us that point P is a fixed point on the wheel. In order for this question to work, point P actually has to be right here. So I'm not actually sure if this is such a great question. I would kind of take issue with it in some ways, just because in order for this question to work, we have to assume P is actually the height right at the center of this kind of cat training wheel above the ground. So point P and the center of this circle, I can do better, are right both at the center. This is the height from the very ground. Okay, so write down the value of c. So c is this constant right here, and it refers to the principal axis. So if I can just maybe I'll try to draw this out. And here, so let's say this is our trigonometric function, and this is the height against time. It starts off right at this midline right here, and then we'll find out later in terms of how it rotates, but it rotates in an anti-clockwise direction, and we'll find out later, how fast it rotates and so, but it's going to have this pattern right here. So this up-down cycle and so on. Okay. And what is what is C in this case? C is what's called the principal axis, or you can kind of think about it as the midline or the average. So a few different ways that we could find this. If we didn't have, for example, this value given to us as 78 centimeters, the midline, you can also find it as max plus min over 2, essentially the average. But since we have this midline of 78, we know that h equals 78, or 78 is the value of c. So once again, what is this value of c? It's the principal axis, the midline, essentially the halfway point between the max and the min. All right. When t equals 4, point P reaches its maximum height of 143 centimeters. Find the value of A and the value of B. Okay. So going back to our function here, what is A and what is B? A itself refers to the amplitude of a function. And what is the amplitude? The amplitude is the height from the maximum to the midline, or essentially the height of the minimum to the midline as well. Essentially from the midline to the peak, or the midline to, well, I guess the trough. Think about it as the height of the wave. In this case, the midline is at 78, the maximum is at 143. So what is A? The distance here of 143 minus 78. And in this case, that would be 65. So 65 centimeters. All right. More generally, I know it's not asking for it in this question, but amplitude, more generally, is given as max minus min, that is to say distance from the highest point to the lowest point, divided by 2. But in this case, we know the midline, we know the highest point, therefore the distance, or let's say the height of a wave, is just given by 65. Okay, part 2 of question B, we're asked to solve for B. B is our frequency. So what is B? B is given by 360 over the period. So what makes these a little challenging is they're not given in the formula booklet, so you got to remember these. 360 over the period. And what is period? Period is the time taken to complete one up-down cycle, one complete revolution. So P going back to its starting point. How long does that take? When T is equal to 4, it reaches its maximum. So here, we know it takes 4 seconds to go from here to here. And we can infer, if this cat is, let's say, traveling at an equal pace or this constant pace, then it will take another 4 seconds here and another 4 seconds and another 4 seconds. 4 seconds to go a quarter, it'll take 4 times as much to go through one complete revolution. Therefore, we know that the period is equal to 4 times 4, or 16. So what is the value of B? B is equal to 360 over 16, which is equal to, in this case, 45 over 2, or I guess we could say, what would that be, 22.5, if we wanted. 22.5 would work as well. Okay. Part C, write down the minimum height of point P. So the minimum would be right here. If we know this is 78, and the distance of a wave, or the height of a wave, is equal to 65, then to get to the minimum, it would just be, well, running out of space here a little bit. 78, the wave itself is equal to 65, so 78 minus 65 would give us 13. Okay. So, once again, midline is at 78. The wave height is equal to 65. 78 minus 65 would take us to the minimum, which would be the height that we are off the ground. Okay. Later, the cat is tired, and it takes twice as long for point P to complete one revolution at a new constant rate. Write down the new value of B. Okay. So before, it used to take 16 seconds to go through one complete revolution. The cat's tired, so it now takes twice as long. That is to say, our period, we could say period new, is equal to 32. And if it takes twice as long to go through one revolution, our period, is twice as long as well. B is equal to 360 over 32, or just dividing by a number twice as big. Instead of having 45 over 2, we'll have 45 over 4. So 360 over 32, 45 over 4. That would be our new value. Okay. Period used to be 16, now it's 32. Value of B is 360 over period, so 360 over new period, 45 over 4. Okay. Gilles charges a customer per hour to hire his boat. It is known that dp dt equals 20 minus 980 over t squared, where t is greater than 0 and less than or equal to 12. P is the cost per hour in Norwegian krone that the customer is charged, and t is the time in hours spent on the boat. The cost per hour has a local minimum when the boat is hired for h hours. Part A asks us to find the value of h. So A is the point at which cost per hour is minimized. So how can we use our derivative to find that out? I'm going to draw a quick sketch to just give an example of how the derivative kind of relates to a quote-unquote normal function, or kind of regular function. Just going to do it for, let's say, y and x. Let's say we have some kind of, what can we say, some kind of cubic function like this. And how can we use our derivative to find a local minimum or a local maximum? So derivative is another word for the gradient function. It tells us the slope at any given point, the instantaneous rate of change. So for example, right here, if you were to substitute whatever this, x value was, you were to substitute this into our derivative function, it would tell you the slope of a line at that particular point. And similarly, if you were to substitute this value, whatever it is, once again, into the gradient function, it would tell you the slope at this particular point. And there's going to be a point where after we have done all of our increasing, positive slope, positive slope, positive slope, before we begin to decrease, our slope is going to be equal to 0. That is to say, we won't have any slope. It won't be increasing or decreasing. So we can find a maximum where our derivative is equal to 0. And using the same logic, for example, let's say here's a point. We can find the instantaneous rate of change. Here's another point. Find the instantaneous rate of change, the slope at this given point right here. And there's going to be a point where, yes, we decrease even more. There's going to be a point where we have no more slope. That is to say, in this case, where dy dx, the slope, is equal to 0. So in the same way, we have done all of the decreasing that we're going to do. Before we start increasing once again, we would have reached our lowest point. So where the derivative is equal to 0, we can either reach our maximum or our minimum. In this case, we can find our minimum by finding the point at which dp dt is equal to 0. So let's go ahead and do that. So question A, we essentially want to set dp dt equal to 0. So here we have 20 minus 980 over t squared, and we want this to equal to 0. So where is the point where the rate of change is equal to 0? So let's go ahead and work this out on the calculator. Menu, algebra, numerical solve. 20 minus, let's open up a fraction here, 980 over t squared, and we'll solve for t. Okay. We need to set it equal to 0, of course. So when does the derivative itself equal 0? All right. When t is equal to 7. So let's write that out. So when t is equal to 7, the cost per hour reaches a minimum. Sandra hired Jill's boat for 5 hours and was charged 328 Norwegian krone. Yvonne hires Jill's boat for 7 hours. Part B asks us to show that the cost per hour for Yvonne is 312 Norwegian krone. So in this case, we want to find the cost per hour. We're told above that P itself is cost per hour, so this function won't work itself. This is change in P over change in T. So we're going to need to find the original function, which just relates P to T, or cost per hour to time. So we have the derivative, and essentially we want to find the original function. To do that, we're going to need to do anti-differentiation. So we're going to need to reverse the process. So let's write out our derivative here, and then we'll use anti-differentiation to find that original function. And then once we have a relationship between P and T, we should be able just to put in the number of hours that Yvonne hires Jill's boat for, and it should give us this value of 312. Okay, so let's go and write this out. So here's our function, our derivative function, 20 minus 980 over t squared. I want to grab this and we'll just make some room down here. Okay, so we have the derivative, but we want to find the original function. So just in terms of p and t. So what can we do? We're going to need to use anti-differentiation. In the formula booklet, we have anti-differentiation, the formula, as f of x equals x to the n. And then if we want to perform anti-differentiation and just find, let's say, our original function, what would we do? Well, it's x raised to the power of n plus 1, and then we would divide by whatever the value of that new exponent is. So if I can write this out in maybe a more familiar way, if we imagine that this is the derivative, this would be our original function. And how do we move from the derivative to the original function? Add 1 to our exponent, and then divide out this whole value by whatever that new value of the exponent is. Okay, so let's go and do that here. It's the final question on a paper 1, so it's going to be challenging. We can't actually yet approach this because we've got this variable in the denominator. So let's rewrite this first. Here we have dp dt. I'm going to make more room. We have dp dt equals 20 minus, and then how can we get this variable out of the denominator? Let's move it up. So it's still minus 90, and then when we move it up, we imagine that this power of 2, or whatever power it's raised to, becomes negative. So remember, we need to rewrite this. We can't take a derivative or antiderivative when our variable is in the denominator at the bottom here. So move it up, whatever the exponent is, just put a negative, and you should be fine. You will be fine. Okay, should we explain a little more? 1 over x is equal to x to the negative 1. 1 over x squared is equal to x to the negative 2. And 1 over x to the n is equal to x to the negative n, just generalizing. Okay. Same idea here. This is 1 over t squared essentially, which we can write as t to the negative 2. All right. Now let's find our derivative. So this is, sorry, not our derivative, our antiderivative. So here we go, 20, this would be 20t minus, so let's go ahead and add 1 to our exponent here. So we have minus 980, and we're adding 1 to the exponent. So that would be only negative 1, t to the negative 1. And then we want to divide this by whatever the value of our new exponent is, which in this case is negative 1. And remember, we have this constant, this unknown constant, when we take an antiderivative. When we do differentiation, it's possible that the constant would have just fallen away. We don't know if there was some constant. Let's clean this up a little. P is equal to 20t. Negative divided by a negative, this would turn into positive. Positive 980t to the negative 1 plus c. We don't really want this constant right here, so let's try to find out what it is. That's where this comes in right here. We know a point on our original function. We know when t is equal to 5, p equals 328. So we can substitute that into our, my goodness, we can substitute that into our original function, and then we would have a relationship where we would have t, p, and then since we know t and p, we just have c left over. So p is equal to 328. T itself is equal to 5. And now we have an equation just in terms of c. So we can go ahead and solve for this. So let's go to the calculator, we use nsolve and work this out. Menu, algebra, numerical solve. 328 equals 20 times 5 plus 980 times 5 to the negative 1 plus c, and we want to find out what c is. In this case, c is equal to 32. So let's go back and write this out. C itself is equal to 32. Since we know that c is 32, let's actually write this in for our function. And this is our final relationship between p and t, right here. Okay, I'm going to erase this part because I don't think we need it anymore. But we might need some more space for this question. Okay, so here's our function relating p and t. What we want to do at the end is show that the cost per hour for Yvonne is $3.12. So Yvonne hires the boat for 7 hours. That means t is equal to 7 and p should be equal to $3.12 if we've done everything correct. So t is equal to 7, and let's find out what p is. T is equal to 7. She rents it for 7 hours. 7 minus 1 plus 32. And if everything is done correct, this value of p should equal 312. So let's go to the calculator and work this out. 20 times 7 plus 980 times 7 to the negative 1 plus 32. And this gives us 312. Okay, so let's write this out. 312, and I guess we can write NOK. All right, so kind of involved question towards the end. Not bad, I suppose. All right, I hope that was helpful, and as always, best of luck.